Okay. Hello, everybody, and welcome to yet another webinar from the Engineering Leaders Series at SimScale. My name is Samir Jabber, and I'm the Content Manager here at SimScale, and I'll be your host for today. And today we'll be talking about a really interesting topic. Recently, we've announced a partnership between SimScale and Hexagon to bring Hexagon's sort of leading nonlinear FEA solver Marc to the cloud and leverage SimScale's cloud native simulation platform. So we'll be talking about that today and discussing it. And but before we do so, I'd like to first of all tell you a bit about what you could do in this webinar. So before we meet our panel, just very quickly, you are in audio mode or listening mode. So in order to engage with us, feel free to access the chat section and introduce yourself. Let us know where you're from and what you're looking for in this webinar. And if you have any questions, you can either ask them in the chat or ask them in the question section that you'll see right next to that as well. And as soon as we get to the end of the webinar, we'll have a nice little Q&A session to answer your questions and make sure that we got everything that you want answered there. So before we jump straight into it, let's meet our speakers. So first, we have Ms. Joanna Lehmeyer, who's the business enablement manager for multiphysics at Hexagon. And Joanna has over a decade of experience developing and validating nonlinear models for applications like biomedical and defense applications. And she focuses on the practical application of computational models. Her work includes creating image reconstruction models and designing test programs for characterizing novel nonlinear materials and for model validation. Now, prior to joining Hexagon, Joanna was a research associate in mechanics of materials at Imperial College London and completed her PhD in mechanical engineering with the Arthritis Research UK Centre of Excellence at Cardiff University. So, Joanna, thank you for being here.
Thank you for inviting me.
Next, we have Jean-Daniel Luquier. So Jean-Daniel has over 20 years of experience in computer-aided engineering, especially in structural simulation. And he's based in France and has worked across a range of positions in the software industry, from support and service to technical marketing and business development. He's currently a product manager for the nonlinear structural solutions at Hexagon, including the Marc software. So Jean-Daniel, thank you for joining us as well.
Thank you for this introduction.
And last but not least, we have our very own Richard Stöcke-Schule, who's the product manager at SimScale. With a background in applied mathematics and mechanical engineering, Richard is a valuable member of our product management team here at SimScale, and he's quite a common face at these webinars if you've watched the previous ones as well. And Richard and his team constantly try to make SimScale a better fit for every engineer in the world. So Richard, thank you also for being here. I think that's all my time now. So I'll meet you all in the chat as the webinar is going, and I'll leave the stage to Richard to kick us off. So Richard.
Great introduction. Thank you, Samir. Thanks for the kind words. Speaking about the common face, I'm sorry, I have a camera malfunction today, so you won't see my face today. And yeah, thank you also to Joanna and Jean-Daniel, who will take part in today's webinar and tell us about Marc and Hexagon and why this is the state of the art when it comes to nonlinear structural. And we'll see hopefully today how there is a great total value addition with the combination of Marc and SimScale. And without further ado, let's start with the overview about today's presentation. So yeah, we want to showcase today why it is kind of a revolution of having the first really well-known commercial nonlinear structural solver available on SimScale on the cloud. What are the benefits for our users, and what are new fields, new capabilities that this unlocks on SimScale. The agenda is quite simple. First, talk about the why. I'll introduce SimScale for the part of the audience who is not very familiar with SimScale yet. And then Joanna will take over to introduce Hexagon and Jean-Daniel will complete that with showcasing Marc's highly nonlinear capabilities, and then we'll go back to see the SimScale platform powered by Marc, and what we can expect from that combination. And in the end, we'll try to save about 15 minutes, maybe 10 for the Q&A, so you have enough time to ask all your questions. And yeah, let's start. So of course, the first question is why is it relevant to have another solver on SimScale? As you might know, we have already quite a few, but let's see where we currently are today. So we have actually some really transformational changes happening right today. We have in the hardware world quite large transformations with respect to electrification, right? Not only in automotive, as a whole transition in the whole energy sector to renewables and everything that is related to that. Automation is more and more prevalent in the whole product development process and cycle. We have new space technologies, a new era that's also happening right now. And obviously we have the growing challenges with the climate change and net zero buildings and cities. And all this happens at the same time as we have also quite fundamental changes or a wave of new technologies on the software side. GPU compute becomes a standard meanwhile in many different applications. We can run simulations at scale that we couldn't dream of just a couple of years ago. Machine learning and AI, everyone speaks about this today in every aspect of everyday's life, but also in engineering. And cloud native is the new standard in a lot of software interactions in your daily life, and so is it for engineering and engineering tools. So to put this as the fundamental context where we live in today, and see what are the actual challenges that then trickle down in the development process. And what we have seen in a lot of discussions with customers and prospects is that speed and efficiency is the #1 demand for engineering organizations today. So the development lead times, the engineering lead times are slashed from years to months, sometimes even weeks today, right? So the project timelines from 2 years to 12 months, even less than that, are a few response times, right? Where you get a request for a new product, a new development, goes down to just a couple weeks. And that means you need to be able to react to these requests pretty fast. So the simulation lead time really needs to be decreased, as well as the simulation cycle time. And how can this be done? Of course, the simulation lead time is the #1 factor. So the time from where you get to know about a new project, new development, new iteration, until up to the first time where you actually can derive insights from a simulation result. And with this, we make this available with SimScale and Hexagon by providing best-in-class technologies that are also robust for the early stage design evaluations. Robustness is a key factor in the early stages because typically that's not done so much by the experts, but more by the designers. They're not very familiar with all the different details of any nonlinear solver and how you can make a non-converging simulation work. So it needs to be really, really robust. Also, something that has already been talked about for a couple of years, basically the idea of democratization of simulation or left shift of simulation. It means that simulation needs to be early and broad, but not siloed. That's our approach here. So we think the solution to the reduction in the turnaround time is first to maintain a centralized quality control of simulation, but have a decentralized use of simulation. So we have a safe environment and robust access to these simulation technologies at any time in the development process. So we have this here in SimScale with the definition or enablement of defining templates, right? So the central simulation team can quickly define simulation templates, which can be consumed by the product and design teams. And finally, unlocking of new next generation engineering workflows. As we just talked about, AI, machine learning is at the core of every new development we see today, and so need the new simulation platforms be ready for these workflows by providing a holistic view on data, on workflows, to enable actually AI training and use of AI models. Yeah, and how this is combined here with our today's speakers and the platforms we're using is Hexagon basically can provide an unseen level of expertise, robustness, and breadth of simulation technologies for structural simulations and beyond. With state-of-the-art solver technology, it has been known since decades. And SimScale, on the other hand, provides a cloud-native and accessible simulation platform. And with that together, we think we can democratize the access to advanced structural nonlinear simulation and empower the engineering teams everywhere and around the world with the new next-gen engineering workflows. So quickly to introduce our company in SimScale and who we are for the ones in the audience that are not very familiar with us. SimScale as a simulation platform currently has about 600,000 users worldwide. We have customers in more than 50 countries. Thousands of academic institutions are using SimScale. And we have millions of simulation projects in production. And all projects having, as I said, they share the same foundation, the same baseline, and are ready to use, for example, for AI training. We have 160 employees, meanwhile, across 8 time zones, so we can also globally enable our in-product customer support. But we're headquartered in Munich, in Germany, where I'm also sitting today. To the SimScale platform, what is it? So SimScale is a cloud-native simulation platform that you can access just with your browser. There's no installation needed, no IT involvement. You get just instant access to the tool by signing up. It's one platform with many physics enabled. We see on the lower right side, we have flow analysis types available on SimScale, coupled heat transfer and CFD, thermal, of course, electromagnetics and structural. And all of this is accessible through a very common standardized user interface. So if you have done a structural simulation on SimScale, there's not a big difference to running a CFD simulation on SimScale. The whole workflow is exactly the same. As SimScale is cloud native, we enable real-time collaboration and real-time support. So you can share your projects you're working on with your whole team. You can edit the project, you can really work together on the product. At the same time, should you face any difficulties or issues, you can immediately access our in-product support. There's a button where you can simply share your project with us and ask your questions in the live chat, and our support engineers will have immediate access to your project and be able to help you. Obviously, the standard is that your project is not shared with anyone. It stays private to you. We use the highest grade security measures, similar to what you do in your banking system, so your data is safe while you have the full accessibility and collaboration capabilities. And of course, the standard with cloud native simulations, you can run it at any scale as you're not limited by your local hardware. We can run dozens or hundreds of simulations at the same time on hundreds of cores each simulation run. And not to forget about the AI-powered nature of SimScale. All data is in a standardized definition in our backend. And as soon as the simulation is run, you can also on SimScale train AI models, surrogate models with your simulation data to be really much faster in the next product iterations, when it just takes a couple seconds to predict a new design iteration. Yeah, and that's basically what we're seeing, what's happening today, and how people are using today SimScale. So we have centralized, typically centralized simulation expert teams that develop simulation templates that they can store it. And the user, as we see on the right side, can simply use the template, import it, and then exchange with their current design and be sure that the whole setup, numerics, and so forth is validated in accordance to the internal Q&A requirements. Yeah, and obviously these templates can be shared with different teams, specific teams, globally in the organization, or just with specific people in the team. And as you start building out your simulation data by just iterating through designs, you automatically are enabled to also train AI models on SimScale, right? You can, with your simulation data that might be, for example, generated by this globe valve template, you can simply go in, search through all your data, collect all the globe valve projects and train within a couple hours and deploy exactly that model then to your peers. And then they can predict the next design iteration within seconds instead of, I don't know, half an hour, what the typical iteration takes. That's what we're seeing here, right? This is then the consumption of the AI model. That's the traditional interface on SimScale, where you on the left side define your boundary conditions, and then on the top right you have the option to select your AI model that you want to use and predict within a couple seconds, right, real time, the key performance indicators of your model. Yeah, and obviously this works for CFD, for FEA. It's independent of the actual physics that you're running on SimScale. Okay, and with that, I'm through the general introduction of SimScale. I'm handing over now to Joanna and Jean-Daniel for introducing Hexagon and Marc.
Can you confirm you can see my screen? Yes, thank you very much. Thank you, Richard. Hi, everyone. My name is Joanna Lee Mayer, and I'm the Business Enablement Manager for Marc here at Hexagon. I'm thrilled to be here today to help announce this exciting partnership between us and SimScale. Thank you for having me once again. It is a great, I think, exciting journey we're about to embark on. So let me first start by introducing Hexagon, the value we hope to bring to this partnership, and why. Hexagon, we're a multinational company and a global leader in providing digital reality solutions. And what this really means is that we try and combine sensors, software, and autonomous technology to provide solutions that allows customers to leverage data to boost efficiency, productivity, quality, and safety in a range of applications. Some of these applications might be industrial, manufacturing, infrastructure, public sector, or mobility. At Hexagon, we're driven by partnership and innovation, and hopefully you'll see just by looking at our manufacturing solutions portfolio alone that, yeah, this is very evident. So this is our manufacturing portfolio. It is dedicated to optimizing manufacturing workflows from the first concept to the final product. We want to enable smart manufacturing. That is one of the keywords we have to drive our innovation. In our portfolio, we have three core areas. We have metrology and inspection solutions. We have production software solutions, and design engineering solutions is where Marc resides. These solutions aim to improve efficiency in product design and prototyping, embedding quality into the product design and ensuring manufacturability and productivity downstream. By prioritizing innovation, our technology impacts 95% of all cars manufactured and 90% of all planes and 75% of smartphones every year. So what is our roots and where did we come from? Our roots is very much in computational engineering and in particular structural simulation. We can almost say it is in our DNA. Our journey first began in 1965 when NASA contracted MSC to develop MSC Nastran. The first commercial version was released in 1971, and in 1999, Marc, the first commercial nonlinear finite element software, joined us. There will be more on this later, and I'm not going to steal JD's thunder. For 60 years, we have been developing simulation software internally and making relevant acquisitions to cover all the physics and other physics that customer challenges, being able to model mechanisms, acoustics, materials, and manufacturing. Today, this portfolio, we have 22 products which are looked after by over 1,500 software developers worldwide. We have an extensive experience in both creating and also connecting simulation tools, providing solutions for accelerating product development and reducing prototyping and testing for larger OEMs as well as SMBs, from automotive to aerospace and everything in between. So let's look at what our offerings can do. Our offerings cover a wide range of solutions and applications. Here are a selected few examples. We provide efficient data management solutions for material data and creating image-based microstructural digital twins to predict composite material behavior. Our topology optimization techniques help in component lightweighting, and our virtual manufacturing suite offers accessible solutions for simulating manufacturing processes. Some of the examples are additive manufacturing and also component assembly, as you can see in the video for the battery pack. Our offerings can analyze and optimize system dynamics, integrate multiple physics simulations for comprehensive multiphysics analysis, and also predict and enhance the durability of components through fatigue analysis, ensuring the robust design for these components. And last but not least, simulate environmental conditions to test and improve product performance. With our offerings, we aim for a rich user experience, smart workflows, streamlined processes, and automation. All of this within unified platforms to promote collaboration across disciplines, share data, and maintain consistency throughout the product life cycles. These attributes set our solutions apart, and we are committed to empowering our customers with cutting-edge simulation capabilities, enabling better designs, faster time to market, as Richard already mentioned, is very important, and superior products. All of these are driven by well-established strong solvers in the background, which we have been developing and refining over decades. Our solvers are optimized for robustness, speed, and accuracy, achieving reliable results with efficiency. So why have we brought Marc, our nonlinear solver, to SimScale? Nonlinearity is all around us in the real world. If we look closely, we can see that everything, in fact, is nonlinear. There are three types of nonlinearity: material, geometric, and boundary condition. Material nonlinearity can be observed in various everyday scenarios. For example, rubber materials in tennis balls exhibit nonlinear behavior. With plasticity, you can see this in metals and plastics, where they deform permanently under stress. Viscoelasticity is present in materials like oobleck and skin, which exhibit both viscous and elastic characteristics. Finally, material failure due to cracking and debonding is another form of material nonlinearity. Geometric nonlinearity is when deformations are large enough to change the geometry of the structure significantly, affecting its response to the loads. Examples include bending of beams, buckling of columns, and flexible structures. And finally, boundary condition nonlinearity arises when the constraints or supports of a structure changes during the loading. This can be seen in scenarios where the contact conditions change, for example, door hinges and bridge bearings. And here we have an example of a washing machine, and if we look closely, there are actually numerous examples in just this washing machine that is the contact scenario which requires nonlinear analysis. For example, sticking of the PCB to the curved console, analyzing the door seal's performance, vibration damping, and even shipping, handling, and stocking of these units. To understand why nonlinear analysis is important, we first need to look at what linear analysis is. Linear analysis, in these types of analysis, we make assumptions, such as materials being linear elastic, undergoing only small deformations, and exhibiting no buckling or failure or contact behavior. Linear models are idealized mathematical approximations that allow us to understand and analyze the complex real-world problems. So with safety factors and empirical data collected over decades, these models are essentially legacy tools that engineers have become very familiar using and are confident that they will be able to design safe products with. These models are highly used because they're scalable. But when we look at the real world, as we mentioned before, it is not so neat. It is not linear elastic. We encounter nonlinear materials and behavior. Materials stretch and they yield. Some are time dependent and they exhibit creep and relaxation behavior. Materials could fail. Components can undergo large deformations. They might buckle, and some products rely on the post-buckling behavior to work. For example, snap-through mechanisms. Components and parts within the structure, they always come in contact. Nothing works isolated on its own, and they interact with each other. You have friction, you have adhesion between these parts. The touching bodies don't just touch, they slide past each other, they stick and they slip, and they can separate in certain conditions. In some cases, as mentioned before, the boundary conditions can also change with the loading. So as the engineering industry explores more innovative designs and they push the design envelopes to the limit, simulation capabilities that fully utilize and exploit these complex mechanical behavior become essential. Engineers need to simulate more designs to design hard, more details to design harder, faster, and in a leaner manner, without relying on repositories of empirical data or producing masses of prototypes. So to describe these behaviors, we have different models. For example, to describe stretchy materials, we have hyperelastic models. For plastic yielding, we have elastic plastic models. And for time-dependent materials, we have viscoelastic models. We can use temperature models to add temperature dependency. For buckling, we have different convergence criteria and incrementation schemes. And for modeling breaking, cracking of things and the crack propagation, we have VCCT and XFEM. We have cohesive sew models to model adhesion. This may all seem imposing, but what I wanted to show is that there is no hurdle to leap for nonlinear analysis, which is quite often the misconception. All these models are essentially just additional bits of mathematics to help capture more of this real-world behavior. And they can be, and often are, added to linear models in small bites. The advanced nonlinear models are built in progressive steps. The additional and more complex equations can make these models more difficult and take longer to solve. However, the approximation is closer to reality. And as we mentioned before in the last slide, engineers are increasingly utilizing these complex behavior in the designs of the products, and being able to capture them in simulation is sometimes essential. Determining when nonlinear analysis is needed can be challenging. It involves balancing accuracy and problem size. But how do we know what to include and how much to include? Is a linear analysis sufficient? Quite often, you can simply, by observing, you might see apparent behavior not being reflected in the simulation model. It could be, you could notice it by comparing simulation results with experimental data, and there's a mismatch. In some cases, unexpected prototype failure can happen during testing, and that's when you have the indication that a nonlinear analysis is required. You may have to leverage knowledge and experience, being able to tell when some nonlinear effects is significant or they are insignificant and won't impact the results or the scenario you're looking at. An example of this, I put a picture of the Leaning Tower of Pisa. The builders did not account for the behavior of the soil under load over time. And after 3 years, the ground started sinking, causing the tower to lean. So this is a famous example where perhaps knowledge and experience would have helped. You may perhaps have to run and conduct comparison studies, running a linear and a linear model and comparing the difference in the results. So the right model fidelity is dependent on the simulation interest and quite often requires investigation. You might not know right at the beginning whether a nonlinear or linear analysis is required. And so because of this unknown, it is crucial to choose a tool which offers this flexibility. On this note, I will now hand over to my colleague, JD, to tell you a bit more about our nonlinear solver, Marc.
Thank you very much, Joanna, for this nice introduction on Hexagon and on non-linearities. So it's my pleasure to be with you this morning, this afternoon, to introduce you the Marc solution. Just to inform you that I will not mention what will be integrated into SimScale, but I'm really here to introduce the current Marc solution, WinTop solution, I should say. So Joanna, you can go to the next slide, please. So for people who don't know, actually, Marc has been the first commercial nonlinear FEA solution created in the 70s. More than 50 years of experiences. So it helps us to be one of the leaders for nonlinear simulations. We have inside our solution a lot of capabilities, meaning plenty of what we call analysis classes, meaning the type of analysis you want to do, from static to dynamic, thermal diffusion structural analysis. So yeah, could be completely multi-physics at the end. As Joanna mentioned, nonlinear material behavior is crucial for this type of analysis. So yeah, we have an extensive library available. And just for you also to inform you that Marc actually is already used behind other Hexagon solutions. So here I mentioned some of them. So for example, SimFact, that is dedicated for a manufacturing process simulation, or DigiMat for material characterization, local simulation, and so on and so forth. Well, some key points about Marc solver. So as I said, it's comprehensive. You can do plenty of types of simulations. I would say that probably you will see almost no limit for your engineering processes. We have a huge library of material models. But what are very specific on the big strengths of Marc is the capability of doing automatic remeshing. I will mention that later on, but roughly speaking, it's about having, during the analysis, the capability to change the mesh accordingly to make sure that we will have accuracy in the results. Contact is obviously very important for this type of analysis, and I will have a slide dedicated for that. And we are also engaged in providing a good solution for HPC with good parallelization. So the first use case I would like to highlight for Marc is obviously elastomer. So Joanna introduced this type of material. Here you have some animation showing some simulations that you can do with this type of material. So obviously this is where you will have large deformation. You will have a lot of changes in the contact. You may have some buckling effect, local, global buckling effect. So yes, those models could be very challenging, and Marc has been proven to be very robust for this type of simulation over the year. And you have here a quote from our customer Interseal. And on the next slide would be actually around a recent use case shared by our customer in Turkey called Yamas. So Yamas is a company dedicated for anti-vibration components for vehicles and so on. And they had recently some structural challenges, especially because of cracking. around an anti-vibration bushings. And so we help them through our reseller, by the way, in Turkey called Bias. We help them to leverage Marc to connect simulation with physical tests, so that they were able to have confidence in their simulation and being able to redesign their anti-vibration bushings to meet the requirements. For this type of analysis, actually, it was a three-step simulation process. First of all, with a thermal analysis used to simulate the cooling of the part after vulcanization. And then there was a first structural static simulation for the swagging process. And finally, different virtual statics tests performed through simulation. And with this effort, so Yamas, our customer, was able to optimize their bushing design. Another large domain where Marc is well known is for manufacturing process simulation. So here you have different examples. Could be about glass forming, cuttings. Cutting is obviously an application where remeshing during the analysis would be very important. That could be the case also for extrusion, for forward forming. But you have also multi-physics like models that could be quite challenging, such as induction heating, and so on and so forth. And here you have one slide dedicated to automatic remeshing. So this is really one strength of Marc Solver. You have a nice, well, actually two examples here showing global remeshing. So when the entire part is remeshed during the analysis, and we have also capabilities to do local adaptivity. So local remeshing, let's say, if you wish, for specific applications. So this is quite unique. We are still developing a lot these capabilities. Right now, we have, for example, a dedicated project for improving the robustness for some specific simulation cases here. And the next topic I would like to discuss is about contacts. Contact is very important for all the nonlinear simulation software for structure. We are probably aware about the different methods that are available for contacts. We mentioned, for example, node to segment, segment to segment, right? And we are developing actually we have developed for many years a new approach called hybrid contacts, based on the node to segment formulation. And the idea here will be to have a double-sided contact with this node to segment approach. This will remove a lot of barriers for adoption for our customers, meaning that as it will be a double-sided contact, it will eliminate the choice between primary and secondary contact bodies for people who are familiar with such issues. So in a nutshell, I would say that it will be easier to use. It will give you accuracy for the first time. You don't have to eventually test different definition for your contact and so on and so forth. So it's really, for us, our flagship for contact, and we'll continue to improve this capability in the future. I was mentioning about Marc solely, but obviously sometimes you need to connect with other capabilities, other solver. So here, this is where we think about co-simulation, for example. So for people who don't know, we are able to connect Marc with, for example, a CFD code to do FSI simulation, so fluid structural interaction. And here it's more an example coming from our customer Tata Motors, using Adams for MBD, so from dynamics of assemblies connected with Marc. And it was all about simulating the door closing event. So just to say that, yeah, and Marc is part of a broad portfolio. We can connect Marc to other software, to other solutions for good co-simulation, multi-physics simulation. And after that, I would like to emphasize you some developments that we have done recently and that we are still doing right now. And the first one actually is also, as mentioned by my SimScale friend, is about also artificial intelligence and machine learning. It's quite special actually. So it's about enhancing super elements. So for people who don't know, the idea of super elements is to have condensation of an assembly or a sub-assembly or a part eventually to have like what we call super elements sometimes, or a sub assembly. And this allow you to model very simply a portion of your model with one single element, let's say. And this is very valuable, but the main limitation for this type of simulation is that these super elements can only be linear. And thanks to machine learnings, we are able to perform design of experiment and then train ROM in order to have more nonlinear behavior for this on top of these super elements. So for this particular case, actually, this was an effort driven by a consortium called Compass, where you have a company in high-tech such as NXP in Netherlands. And we were able to use the machine learning capabilities to put some temperature dependencies into those super elements. So this is very useful for the semiconductor industry, especially because, as you can imagine, you have the PCB with different components on top of this. And each of those components could come from, for example, partners. Each partners could have their own way to model and to model their different packages. And so this is an easy way to share the behavior of their packages to NXP, that is the final assembler for the semiconductor industry. The second example I would like to share with you about new functionalities is around contact. So I mentioned about hybrid contact. That is really one key topic for my R&D nowadays. Another important topic for contact is obviously the friction models. You are probably familiar with the Coulomb model used for a long time. And here we were able to enhance this model with some smooth transition between the static friction behavior and the dynamic friction behavior. So very complex nonlinear friction model, for example, used for simulating both self-loosening analysis. Yeah. Still under contact, so maybe you are familiar also with fluid pressure penetration modeling. So this has been also implemented recently in Marc. The idea here would be to simulate the penetration of the fluid between two contacting bodies, and yeah, obviously the idea is to see if there is some leakage risk associated with some seals, for example. So this is very useful for different industry. You have a list of use cases where it could make sense. But yeah, so this is very useful and works well with large deformation, as you can see with the picture at the right-hand side. And finally, my last example is dedicated for batteries. So batteries are important nowadays and are quite challenging. So I don't know if you're familiar, but you have a battery breathing issue that could happen. We say sometimes battery swelling, but the phenomenon is that you have lithium-ion intercalculation process that during charging and discharging, you have the battery that will change its volume. And this could be quite challenging for the manufacturing of the battery modules, battery packs. And this could lead also to some structural integrity issues during the life of the vehicle. And it's quite a complex phenomenon. It's about electrical, thermal, and structural phenomenon. If you want to really model this precisely, this could be quite a mess actually. And we are working actually to propose to the market a more engineering way to do it with some simplification in the physics through subroutines, but yeah, to allow the cells manufacturers to be able to really assess what will be the swelling behavior of the battery cells. So I hope those was very good examples of the usage of Marc. Marc and his graphic user interface called MANTAD are really dedicated for CAE experts. We have recognized that obviously nowadays a lot of people would like to go to web-based application, to cloud-centric, cloud-native applications. And this is where we are very happy to work with SimScale in order to integrate some of those technologies I just highlighted to you, and others obviously, to their solutions. And with that, I will pass the ball to Richard, I guess.
Yes, I hope you can hear me again. Thanks very much to JD and Joanna for this very in-depth presentation of nonlinearity in general and how Marc solves it, and what is a very impressive feature set and the capabilities of Marc. So I think we got a good impression of that. And I'll try to make it short now to leave some minutes towards the end for our users for the Q&A. But I think one question that we haven't really answered now is like, what will the integration look like of Marc and SimScale, right? So on SimScale, we have basically the whole stack of infrastructure. We have the methods from CAD editing, import, meshing, the solvers, the PDE solvers, but also the AI solvers and the post-processing. And we have the different physics, right? We have structural, fluid, thermal, and also electromagnetics. And they're presented to the user via our standard workbench with the browser. You can access SimScale also with an API. And this can also be used, obviously, to integrate SimScale within a third-party application, which we have done with a couple of partners already. And with that, SimScale really provides the whole breadth of applications from very early stage concept designs up to the late stages in the product development and the operations. Where Marc comes in is, it comes in as a layer in the solver technology, as a new very capable solver that broadens the application areas of SimScale in the structural field, and also deepens the applications, right? So we can have more advanced features, more advanced contact handling, stricter coupling between thermal and structural phenomena, and so forth. And this means we can do actually now a more robust design optimizations. So we've seen Marc is very robust for all the nonlinear applications, and it's specifically interesting when you do early stage design optimizations. You need to do many iterations, and the solver needs to be robust with respect to small design changes or even big design changes. You don't want to have every second simulation fail and figure out what to do about it. We can enable more broad simulation-driven designs, right, of use cases or phenomena that we couldn't model before with SimScale, right? We get a new, highly trusted solver, so we can expand on being more trusted on the design validation and provide more accurate results there, and also go into the advanced manufacturing processes that we have just seen a glimpse of in JD's presentation. So a couple of applications where SimScale is already used today and how that will be probably impacted the first by the integration. We see here ITW Global Fasteners, one of our customers that use SimScale for nonlinear pushpin and fastener designs. So they use SimScale to design these fasteners and optimize them with respect to the forces that are applied to insert and extract them, the level of plastification or damage that is created during these processes, and so on. So with that, obviously, a robust solver with respect to the contact solution, but also then the nonlinear material modeling is really crucial. And just as an example here that we did in the past already, this simple pushpin where you push it in and pull it out and measure the forces during extraction, and then in the end have some residual stresses. So this is modeled with an elastoplastic material, second order elements on SimScale. And currently, or with the old solver, it took about 2 hours, right, on I think 8 cores. With Marc, the exact same mesh, the same settings, the same material definition, and so on SimScale takes only 13 minutes, right? So that's 80% reduction, more than 80% reduction in the runtime and in the compute cost. And this is significant. When you do multiple design iterations, you can suddenly do many design iterations in a day instead of a couple. And then on a very similar example here, a plastic push rivet, right? In this case, also nonlinear material, slightly simplified with the elastic but perfectly plastic behavior, where you can really now assess what are the actual separation forces that this rivet can sustain, right? So what is the maximum force that can be applied without the part breaking or being damaged? So here we can see the full insertion process and then all of the separation. And you see on the right side the extreme deformation that the solver can compensate here and can resolve while staying very robust, right? So with the default settings, with the standard contact definition, standard numerics that we'll have with Marc on SimScale, you can run this case on a first try. And this is really something that brings these nonlinear applications on SimScale to a new level with Marc. Obviously, just a final remark, Marc on SimScale will not be your local installation of Mentat just in the browser window. We will not support all the 5 million features from which we have seen a couple today from Marc in the first week. So we'll focus on certain applications and areas, mostly the ones that we already have a lot of customer demand in. And it's in automotive, and fastener, and sealing component design, consumer products, right? Drop tests, standard application, electronics, connectors, and industrial machinery. And for this, we'll have initially the robust contact handling, obviously available from Marc, that can evaluate contact pressure, large sliding, large deformation, friction, obviously, and self-contact. Self-contact is a critical feature when you have rubber components with very large deformation. Obviously, the material behaviors are the initial ones that we also provide today, elastoplastic and hyperelastic materials, and the loads also, as well as the constraints, the standard ones that are available. We'll have automatic time stepping, cutbacks, and have the 3D output of the results, as you can see here. Obviously, a few features will not be there in the initial release. We will not have the fully automatic remeshing capabilities, the nonlinear remeshing there initially, and also the advanced machining, XFEM, fracture mechanics, or composite modeling capabilities. These will come over time, and I'm sure they will bring also high value once they're there, and also these advanced strategies like coupled fluid structure interactions will not be the focus of the initial feature set, but that's roughly what you see here. Okay, finally, before we go to the Q&A, here is a short QA code. You can apply for the early access program. So there will be a closed program initially to evaluate SimScale with Marc, or Marc with SimScale, for the first months. And you can apply on the website. You can search for on SimScale on the product pages with our partners, and then on the Hexagon page, you'll find a form to sign up and apply for the early access program. So if you have any applications that are similar to what we've seen today, that require large contact, deformations, nonlinear materials, friction, self-contact, we're really happy to take you into the early access program and explore how your cases can be solved with SimScale, and you can already then test also the integration on the web on the platform. Okay, so let's quickly jump into the Q&A.
All right, so thank you, Richard, and thank you, Joanna and John Danielle, for the insightful presentations. Really impressive stuff there. We have received a lot of questions, so I hope over the next 10 minutes we'll manage to answer as many of these as possible. And if we don't manage to answer all of them, you don't worry, we will we'll get back to you via email afterwards as well. But some of these questions, in a way, have been answered during the presentation as well, which is nice. But I'll start with the first question here we received. Someone interested in beam and shell modeling, right? And they're asking if there's such sort of beam and shell elements available in Marc or in other solvers on SimScale as well. And this person also alluded to interface conditions such as friction, right, and bonds or whatever. I think John Daniel, you alluded to these in your presentation as well, in the when you were talking about context. So speaking of beam and shell elements, maybe a question to you, Jean Daniel and Ricard. Anything to answer on that when it comes to what's available on Marc and SimScale?
So maybe I can start for the Marc side. So in Marc side, everything could be done. So meaning you can model with beam, shell, solids elements, no problem. And for contact, actually, just to say that, yeah, we can do glued contact, touching contact, contact that is first touching and then being glued because of different physics or mechanical phenomenon. You can do bonded contact, debonding also you can do. So yeah, basically everything is available.
Yeah, and on the SimScale side, we currently support 3D elements only. So no structural elements at the moment. We're working on enabling this, but we're really focusing on the use cases where 3D elements are sufficient. There's strategies to also use 3D elements for thin parts. So it depends really on the use case if shells are required or not. But fundamentally, all the analysis with structural applications are currently limited to 3D elements.
All right. I hope these answers answer your question, but let's jump to the next one. This audience member mentioned two use cases where he's having some challenges when it comes to nonlinear analysis. One is drop testing, right? So looking into that, we talked slightly about that in the presentation when it comes to contact issues and plastic material. And the second is vibration analysis, right? So this person is finding trouble with nonlinear contacts such as faces, which cannot be they could be penetrated or divided. So is this a possible use case for the Marc solver on SimScale?
Yes.
Yeah, please.
Yeah. Yeah, we will start with the static analysis and the thermomechanical applications on SimScale. We'll add then obviously also the transient dynamic applications. So the complexities that come with contact together with dynamic effects and nonlinear materials should be easily solved with Marc and SimScale. That's exactly the type of applications we're looking after.
Yeah, and just to say that, well, especially for the first part of the question for drop test, this is where sometimes people are looking at implicit versus explicit software. So Marc is an implicit software. It's used also for drop test-like applications, but sometimes explicit will make more sense. It depends on the loading conditions, basically the initial velocity, how it will behave, and so on and so forth. And for the second question, well, I would be pleased to have more details on the use case because I'm not fully understand why he was talking about faces that can be divided. But yeah, so more, I would be happy, sorry, to discuss more in details on this use case.
That's great. Then we'll get back to you then with some questions, and maybe Jean Daniel can help answer these questions as well, and also Ricard from SimScale's side. I'll jump very quickly to the next question, and it's an interesting question here. So someone is asking what differentiates SimScale and Marc, or this collaboration of Marc on SimScale when it comes to model generation and solving nonlinear problems from other platforms or software out there. So especially when it comes to product development in biomedical devices. So we mentioned there in one of the recent slides about stents and valves and stuff like that. So what kind of differentiation can we see from other software? I mean, one thing that I would answer very quickly is accessibility, but I'll leave that to you guys to answer. Maybe Ricard, you can go first.
Yeah, so the question was specifically about Abacus and the comparison between Abacus and SimScale and Marc. I think I'll leave JD to talk about maybe the comparison on the nonlinear side between Marc and Abaqus. But a fundamental difference with Marc and SimScale is you get the accessibility and the free of constraint solution on SimScale. So you can run the simulation on up to 192 cores with Marc and SimScale, right? With the standard license that you get on SimScale, you can run 100 simulations in parallel as well, right? So this comes as a standard feature set of being in the cloud, being cloud native, as well as all the collaboration support as well, right? So you will, even with Marc, there will be a situation where a simulation doesn't converge on the first try, and you might want to ask someone, right, how to solve it. There will be a SimScale support agent within a couple seconds available that can look at your case without transferring any data. So I think that's fundamentally the difference on the accessibility and how the tools are delivered, right, versus a local Abaqus installation. And I think JD can maybe elaborate a bit on the non-linearity and the capability side for medical devices, stents, crimping.
Yeah, well, quickly. So, of course, Marc is not the only one nonlinear solver available in the market. You mentioned another one. Obviously, this is also a very good FES solver. No issue for that. You will have, for example, cases that are not available or not manageable by one solver, or ones that are available by a competitor but not by Marc. So, for example, just to give you briefly an example, it's about when you talk about ablation and pre-releases. So we have unique capabilities available in Marc, but the main differences, I think, will be around strategies, right? So I mentioned briefly about Marc developments around contacts, and I think here this is where you will see definitely differences between what we are, well, how we see contact for the future for simulation versus the competition. So yeah, I would say the main difference would be around the strategies, how we want to go to the market. Richard talk about SimScale approach for cloud-centric application. This is definitely where you will see big differences.
Great, thank you for that, Jean-Daniel. We're getting right at the end of time, but I'll squeeze in one quick question to you, Richard. A yes or no question. Is the Marc solver option available to existing SimScale customers?
Yes and no. So we have on SimScale the capability, and we'll enable Marc for everyone for testing. Marc itself will come as other advanced solvers already on SimScale with their own licensing. So there's basically a base SimScale license, and then depending on your need, you might add a lattice Boltzmann solver for a CFD. You might add an advanced CFD solver for pump applications, or you might add Marc for advanced nonlinear simulations. Not everyone needs it, so it will come as a separate module that you can use, but everyone will be able to test it. And yeah, so the pricing as well, that probably will also be a question, is very similar to all you have seen on SimScale, right? There's a subscription fee, and that comes with compute capacity. And if you would need more specific compute capacity, you can get more core hours basically for your applications. There's nothing changes fundamentally on the licensing model on SimScale with Marc. That's as we do with all the other solvers we have.
Right. All right. We're out of time, so I won't push further with the Q&A, but for all the questions that we haven't answered, we'll reach out to you with answers after the webinar. But thank you for joining us. Thank you for our speakers for really insightful presentations. It's been a real pleasure and amazing insights as well. And just to reiterate what Richard was saying, join the early access program to learn more about this and see how you could make use of this. So you can scan the QR code or just go to the links that we have on our website that feature this program. And we really look forward to learning more about what you do with nonlinear analysis and see how both Hexagon and SimScale can help you solve that. So thank you very much for joining us, and we look forward to seeing you in the next webinar as well.
Thank you.
Thank you.
Thanks,
JD. Thank you, Joanna. It was a pleasure having you.
Pleasure also on my side.
Thank you very much.